Good day, my name is Robert Clark and I'll be presenting my final year project, the flow topology around an aircraft body, as supervised by Professor Beric Skews. This will be for consideration of the Aeronautical Society of South Africa's Best Final Year Project Award. Shockwaves around an aircraft body have been of particular interest of late due to the disturbance they cause on the ground, referred to as a sonic boom. There are regulations pertaining to the sonic boom that are currently prohibiting supersonic civil transport over land. Thus, shockwave research is largely into shaping and ultimately reducing the ground shock overpressure signature of an aircraft. This graph here shows the near-field pressure signature of an aircraft. This very colourful image shows the research NASA has completed in this regard by shaping an F-5 aircraft to reduce its ground shock signature. What should also become immediately apparent is the great complexity of the flow field around an aircraft. Due to this complexity, the typical approach used in gas dynamics research is one of reductionism. This essentially involves breaking a problem down into its fundamental parts and analyzing these already complex flow fields in isolation. For instance, an ogival body might be analogous to a fuselage, or two wedges might simulate the flow around an inlet. The purpose of my project, therefore, was to better understand the full flow field around an aircraft body. Consequently, the objectives of my project were to have an aircraft body model manufactured for experimental testing in the Witwatersrand supersonic wind tunnel. A CFD model, or computational fluid dynamics, of the same aircraft was also required to be made. The CFD and experimental results were required to be compared, after which both could be used to qualitatively analyze the flow around the body. The qualitative analysis would yield the ability to determine what effects resulted from the configuration rather than the constituent parts. All experimentation was conducted in the Witwatersrand supersonic wind tunnel. The model, as shown here, was designed to emulate a typical supersonic delta wing aircraft. Schlieren photographs were taken of the flow around the body from different angles. Surface oil flow visualization techniques were also used. The CFD models were three-dimensional with a fairly high cell count. Therefore, all the solver processes were computed at the Centre for High Performance Computing in Cape Town. 3 models were run, 2 in VISID and 1 VISID model, all with adaptive meshing, the effects of which can be seen in the complex mesh here. In terms of the results, the model was experimented with 2 angles of roll, 0 and 90 degrees, effectively a side and plan view. The side view is shown here. The experimental image is 2 Schlieren photographs overlapped, as the aircraft is too long to photograph in a single picture. The CFD and experimental results are fairly similar, although it is difficult to say to what degree. The wing leading edge shock was difficult to detect, as it was a weak shockwave and is at an oblique angle to the light rays passing through the test section. More information can be obtained when comparing the experimental and computational results for the plan view of the aircraft. Comparing the images becomes easier when you put them together. The CFD and experimental results can be seen to be remarkably similar, with the lines of density gradient in the 2 images coinciding. Some flow features of note are A, the bow shockwave coming off the nose of the aircraft, B, the expansion wave centered on the corner of the side of the fuselage, C is the shockwave shed off the leading edge. This is only visible outboard of the wing as the leading edge is supersonic, meaning that it is swept outside of the bounds of the Mach cone. D is an interesting feature that is actually a partially circular shock originating from this intersection between the vertex of the wing and the fuselage. The effects of this shock were also detected from the surface oil flow patterns. You can see how the shock affects the surface pattern both in the CFD and experimentation, with a region of dense concentration of the surface streamlines. Essentially, the shockwave exists to realign the flow over the wing with the fuselage. Cross-sections were taken through the flow at several points along the body, a valuable tool in interpreting the flow field, with several complex, interesting flow features appearing. For instance, this image shows the cross-section taken just aft of the leading edge fuselage intersection. The low-density, butterfly-like pattern marked as A arises from the overlapping curved expansion fans originating from the corners of the fuselage. This image shows another cross-section after the trailing edge of the wing. This cross-section demonstrates a bit more of the three-dimensional complexity of the flow around the body. The leading and trailing edge shocks, A and B respectively, are both visible in this image. The expansion from the vertex of the wing is also shown, indicated by the region C. All the shock and expansion waves are coiled around the tip of the wing due to edge effects. The wing is not producing lift, so there are no tip vortices. If present, however, these would likely interact with these structures. Also of interest is the circular shock I was referring to earlier, marked by the point D. It could be concluded that there lies a significant future for gas dynamics research into aircraft-like bodies, which allow a greater understanding of the big picture, the larger, far more complex three-dimensional flow field around a real aircraft. My project was all about bridging the gap between gas dynamics research and the real world of supersonic aircraft, and I believe it has achieved its objective successfully. Thank you for watching.